Okay, finally, you recall from last time that two sets are disjoint means their intersection is the null set. A generalization of that is, suppose I have a set of subsets. So A1, A2, and A3 dot 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 are all subsets. Well, we say this set of subsets is pairwise disjoint in case if I take any two of them, one or two things happen. Either they're the same set, in which case I could throw one of them out, or they don't intersect at all. All right, so pairwise disjoint means that if I take any two and intersect them and I do not get the null set, then they have to be the same set. Okay, that leads us to the following definition. A partition of a set A. So I'm going to take a set A and I'm going to partition it up. So I'm going to break it up. Now, if you think about partitioning a room into pieces, what is the property of those pieces? And I'm going to claim one property is the pieces don't overlap. Another property is if I add up all the pieces, I get the whole room again. And the last property is none of those pieces are empty. All right, and that's exactly what the three criteria for a partition is. So what's a partition? It's a set of subsets that satisfy, number one, that set of subsets is pairwise disjoint, like we just talked about. Number two, if you union everything up, you get the whole set A. And finally, number three, none of the subsets is the null set. Okay, so a partition on a set A is a set of subsets that satisfy these three things. So let's partition a set up. Let's suppose A is the set ABC. What would a partition of A look like? Well, there's lots of partitions of A. So you just don't have one. And all you have to keep in mind is that it has to satisfy these three things. Namely, any two are disjoint. This says that every element in A has to appear in one of those sets. And this one says none of those sets can be the null set. All right, so here's one partition of the set ABC, right? I could break it up like this. Have the set A and then the set BC. That satisfies all three criteria. Okay, if I union them up, I get all of A. I don't see the null set in there anywhere. And this set is disjoint from that set. So there's one partition. What's another one? Well, let's look at another partition, P2. I could have the set C and the set AB. Right? Every element from A is in there somewhere. The null set's not in there, and they're disjoint. Partition 3, might be the set AC and the set B. Partition 4 is oftentimes forgotten. It is the set ABC, so I just have just the set itself. That fits the criteria for a partition. And if I think about it, partition 5 would be the set A, the set B, and the set C. So those three subsets, again, would form a partition of A. After you think about it for a little bit, you'll probably convince yourself that these are the only 5 partitions of the set ABC. It's a reasonable question to ask, how many partitions does A have in terms of the cardinality? And in this case, we saw that if A was cardinality 3, there were 5 partitions. The first person who figured out the general rule or formula for how many partitions given a set of cardinality n got his name on it. And it is called the Bell number. So the Bell number is the number of partitions for any particular set. Finally, I want to talk about how Venn diagrams can be useful for set theoretic problems, and I'm going to do that in the context of the following example. Suppose I surveyed 300 people, and I found out that 100 had smartphones, that 150 had car GPSs, and that 75 had both. Well, I claim that with this minimal information, I can tell you anything about the survey. Now, how do we do it? And the answer is, well, we just draw a Venn diagram. So let's draw an arbitrary Venn diagram for 2 sets. Let's say this, the set S, are the ones that had smartphones. Get it? And let's set G the set of people that had GPSs. And so when you simply work from the inside out. If I say 75 had both, then that meant 75 are in the intersection, right? So I've got 75 in there. Now, if I knew that there were 100 with smartphones, then the smartphones would be, these 2 circles, one of which is 75. It must add up to be 100, so I can tell you that 25 is in this piece. Similarly, if 150 had GPSs, then the number in this circle should add up to 150. But I know that 75 was there, so that means 75 has to be in this set. And then, to try to figure out how many do I have outside, I add up all of these on the inside, which turns out to be 175. And I take the 175 and I subtract it from the total number of people in my survey. And that gives me 125. Hence, there are 125 sitting out here in the boundary. Now remember, this is not the universal set. The universal set contains everything. All right, now my claim is I can answer any question you might have. For example, how many had neither? And the answer is what? Well, the ones that didn't have cell phones or smartphones and did not have a GPS, those are out here. So the answer to that question would be 125. Or I could ask, how many had smartphones but no GPS car? But no GPS. So how many had smartphones but no GPS? Well, the answer would be this set, right? Smartphones but no GPS. So the answer is 25. You see, any question you want to ask, I would be able to answer just by this arbitrary Venn diagram. Now I want to talk about the Cartesian product of two sets, so A cross B. You probably have heard about Cartesian product before when we're talking about the Cartesian plane. And if you think about the Cartesian plane, every point in the plane is represented by an ordered pair. So that really is what the Cartesian product is. If I have two sets A and B, what do I mean by A cross B? I mean it's the set of all ordered pairs A comma B, where A comes from big A and B comes from big B. So if you want to look at a particular example, if I take the set 1, 2, and I cross it with the set AB, I get a set of ordered pairs. What are they? Well, 1A, 2B, 1B, and 2A, right? So I get 4 ordered pairs out of that. Let's look at another example. If I take the set ABC and I cross the set 2, 3, then what ordered pairs do I get? Well, I get what? A2, A3, B2, B3, C2, and C3. So you see that if this set has cardinality 3 and this set has cardinality 2, then how many things are in the cross product? 1, 2, 3, 4, 5, 6. In general, it's not hard to see that the cardinality of A cross B is simply the cardinality of A times the cardinality of B. And simple little formula. Now,